Yeah, good morning, good afternoon, good evening, everybody. It's Wednesday, it's EMinar Day, and it gives us great pleasure to have Hannah Peterson talk to us today on a case study comparison of airborne EM data over two magmatic nickel deposits. Before I introduce Hannah, just a reminder for those of you who are newish here, that you can go on the MTNet EMinar website and you can see links to previous recordings and previous presentations, and you can register for upcoming EMinars, and we have EMinars through to the end of June. A quick advertisement for next week's EMinar that will be at the same time from Carl Kapler. Are the electromagnetic precursors to earthquakes? Two statistical studies from the San Andreas Fault. This should be really quite an exciting presentation. And today we have, as I said, we have Hannah Peterson on a case study comparison of airborne EM data over two magmatic nickel deposits. And I'm very pleased that we're getting this presentation because we don't really have enough EMinars on mining related geophysics, and we don't really have enough EMinars on airborne EM data. So it's wonderful to have Hannah present this today. Very quickly, Hannah is currently employed by Condor Consulting in Colorado as a project geophysicist, earned a BSc in geophysical engineering at Mines in 2017 and a master's at San Diego under Steve Constable. Hannah's also worked in the near surface geophysics, a field geophysicist in southwestern US. Okay, I'll stop my share, Hannah, and hand over to you.
All right, we all good?
Yeah,
there?
that's good. Everything's good.
All right. Minimize this. All right, thanks for the introduction, Alan, and thanks again for letting me speak. This is my second EMinar, but it's been about a year and a half, so I'm excited to get to present to this audience again. So like Alan said, I'm going to present a case study comparison of airborne EM data over two magmatic nickel deposits. One of the deposits is going to be more of a classic magmatic sulfide deposit, and the other has a more unusual deposit and geologic environment. So what I'm presenting today is work done by me and my colleague Blake Cross. You can look for our paper in the Leading Edge this past April issue. There is a special section on critical minerals, and we fortunately got our paper published in this issue, which was pretty exciting. And overall, the paper highlights the geologic and geophysical differences between the two deposits and considers implications for future targeting. So a lot of what I'm presenting today is in the paper. So I'll point you to that for maybe more information and a couple of the figures and references. So, and if you're at the roundup or the PDAC this year, you might have seen a version of this talk. I think those were a little bit shorter, so hopefully reaching some new audience members and adding some new flavor to the presentation. So nickel is considered a critical mineral in the US and Canada, and has increased demand due to its use in electronics, electric vehicles, the aerospace industry, and the solar industry, and has many other uses as well. So I think when most people think of critical minerals, they're thinking of, electric car batteries, energy transition, which is a big part of it. But I thought it was interesting that as we improve and grow other industries like aerospace and even healthcare, it becomes increasingly important in those technologies as well. So with the growing demand, it'll be important to meet the needs of these industries, and that starts with mineral exploration. So that being said, lithium ion batteries are increasing in demand every year with the growth of electric cars and other electric vehicles. And so in this industry alone, the demand for nickel is thought to, or it's going to triple. So right here, the laser pointer, we're sitting at here, 2023, but then by 2030, as you can see in the orange, that the demand is only going to increase more and more and thereafter. So increased exploration efforts are crucial, as well as more efficient and sustainable resource extraction as well, going forward to meet the needs of this industry and the others that I mentioned. So what our study is going to focus on is kind of a fresh and interesting look at exploration techniques for nickel deposits. And like I said, we're going to have two kind of different types of deposits. And the aim for this was just to help to create a different mindset on exploration techniques based on your deposit type. So the majority of modern nickel exploration targets are magmatic sulfide deposits, and this is typically with high sulfide content greater than 10%, so kind of 10 to 90, up to 90% sulfide. And magmatic sulfide targets have historically been good geophysical targets given their strong EM response, but we can expect that a lot of the easy large deposits have been found already. And nickel laterites is another common source of global nickel, but these actually aren't as common in the US or Canada. However, they are more abundant in like Brazil, Indonesia, as you can see on the map here. So meeting the future nickel demand might require readjusting the exploration practices used when looking for deposits, and especially when looking for these for less common nickel deposits and lower grade deposits. Our study areas, so we looked at two nickel deposits, one called the Turnagain deposit in northern British Colombia here on the left, and then the Mayville, it's called the M2 deposit in southeast Manitoba here. The Turnagain property is currently owned by Giga Metals, and the Mayville property currently by Grid Metals, which was formerly Mustang Minerals. So the Turnagain deposit was discovered in the 1950s as just rusty weathering exposures, which was then followed up by geologic mapping, drilling, and then geophysics. And then the M2 Mayville deposit was also discovered in the 1950s, but directly through drilling, and then was followed up with ground geophysics and eventually airborne geophysics. This is a plot showing major nickel deposits. We have the nickel grade on the y-axis and ore resource amount on the x-axis. So we have a lot of the major nickel deposits plotted here, like Boise's Bay, Sudbury, and then we also have, not labeled, but a lot of the convergent margin nickel deposits that have been discovered. And as you can see, these are typically lower grade and a smaller resource amount, but like I said, as the demand increases for nickel, these types of deposits might be more economical to extract. So the two deposits we're looking at, the Mayville M2 is a classic nickel-bearing magmatic sulfide deposit and has extensional related magmatism. And then the Turnagain deposit, which is a more unusual nickel-bearing Alaskan-type intrusive complex that has a convergent margin setting. So as you can see, the Turnagain deposit has a pretty high resource amount as compared to the Mayville that is much lower, but the two have a similar grade, 0.23 and 0.21. So I'm going to move into some of the background geology for the two properties, and starting with the Mayville. So the Mayville resource and the property is located in the Bird River Greenstone Belt. The Greenstone Belt is mostly east-west trending. It's Archean and consists of metavolcanic rocks and platform-type sedimentary rocks. The belt is bounded to the north by granites and gneisses, and this forms a typical, to the north and south by granites and gneisses, which forms a typical superior province assemblage. Across this greenstone belt, there are numerous nickel, copper, platinum group element, and chromite resources that have been identified within 9 mafic and ultramafic intrusions. And the entire greenstone belt is about 75 by 20 kilometer area. So it's a pretty large prospective area for mineralization. So the largest of the intrusions within this belt is the Mayville intrusion. And this is on the furthest north branch of the greenstone belt. It spans about 40 kilometers wide east-west and anywhere from 1 to 4 kilometers north-south. And here, supercrustal rocks are mainly composed of pillowed and flowed textured volcanic rocks. It's bounded to the north by felsic to intermediate orthogneiss, and to the south by more mafic to intermediate metavolcanic rocks. Syn to late tectonic felsic intrusions included pegmatite granites and rare earth element enriched pegmatites. Here, as you can see in the property geology map, the faulting is mostly south, southeast. And one thing to note is that the upper and lower contacts of the Mayville intrusion are not exposed. So the intrusion has undergone green schist and amphibolite grade metamorphism. It's divided into 2 zones. So spot's a little confusing because it looks like a depth section, but it's actually a north and south section of the intrusion. So the upper 700 to 800 meters consists of gabbroic and anorthositic rocks with a variety of textures, including massive and metacrystic gabbros. And then the lower zone here in red is a heterolithic breccia zone. And this is where the M2 deposit is actually hosted. And there is also a platinum group element zone in here as well. This is where you're going to have the massive and disseminated sulfides present. So specifically, the mineralization here at Mayville, like I said, it's nickel copper sulfide mineralization hosted in the heterolithic breccia zone, and this is just below the structural hanging wall mafic volcanic rocks. So here the sulfide minerals consist of chalcopyrite, pyrrhotite, and pentlandite, and some pyrite in a variety of textures, anywhere from disseminated, vein, massive, and semi-massive sulfides. The massive sulfides are thought to be more iron and nickel rich, containing more pyrrhotite and pentlandite, and then getting down to the more disseminated sulfides are more copper rich, containing more chalcopyrite. So the M2 mineralized zone, which is outlined here in black, has been intersected by drilling for a strike length of 600 meters and a vertical depth of 300 meters. And the average true thickness is reported to be about 40 meters. And there's also 2 other mineralized zones, the M3 up to the north here and the M4. I'm mostly going to be focusing on the M2 deposit here, but just wanted to point out that there are other mineralized zones in the area that have been intersected by drilling. And then there's also, like, as I mentioned, a platinum group element zone just to the southeast of the M2 deposit. So this is a cross section through the deposit where we have, sorry, the text is a little bit small to read on the cross section, but the M2 mineralized zone is in red here. The green is mafic volcanics, and the purple is the Mayville intrusion. And here we have the M2 zone dipping towards the south. And in this model, it extends to kind of in between 200 and 250 meters below ground surface. But what we'll see in some of like the Z10 data that I'll show in a few slides, it might actually extend further than this. But to our knowledge, this is the furthest that they've intersected it with drilling, and that just might be the limitations of the depth that they're able to drill right now. So now I'll move into the geologic background at the Turnagain property in British Columbia. So the Turnagain property indicated with this red star here lies on the boundary of the Casnelia and Yukon-Tanana terrains and is adjacent to the Cassiar terrain. So it's kind of sitting on the conjunction between the two, a few different major terrains. It's bounded by a couple of major faults, and the surrounding rocks include graphitic phyllite, which is strongly pyritic and graphitic around the Turnagain intrusive complex, possibly volcanoclastic rocks to the south. And then there are dioritic and granodioritic rocks that outcrop south. So here there are two emplacement theories that exist. Supercrustal or supersubduction setting on a cratonic margin, and imbricated rocks thrust onto a margin of the North American craton. So overall, the Turnagain deposit is in a more of a convergent margin setting, which hasn't historically been prospective for nickel deposits, just given the kind of the geologic ingredients that we have here. But the Turnagain, as we saw a couple slides ago, is a pretty high tonnage deposit, and this can be these types of deposits can be more economical to be mined going forward. So there are a couple other more Alaskan type ultramafic and mafic intrusions on this map, and then there are more up in the Yukon area and in Alaska. So kind of windowing in on the property geology at Turnagain. So as I said, the Turnagain complex exhibits characteristics of a typical Alaskan type intrusion. And this includes a steeply dipping dunite and wherolite core. So it's thought that the sulfur saturation necessary to precipitate a nickel deposit was most likely reached here when the intrusion interacted with the host carbonaceous phyllite wall rocks. It is unusual that it's mineralized here with nickel, cobalt, and PGE sulfides. And the sulfides here in the Turnagain complex are primarily magmatic. There's disseminated mineralization here, rare sulfide, matrix, breccia mineralization, and rare net textured mineralization that occurs in the dunite and wherolite. The principal sulfide minerals here are pyrrhotite, pentlandite, and chalcopyrite. There is some trace bornite as well. There were 4 intrusive phases that occurred here in the formation of the Turnagain intrusive complex. They're listed on this map here, the first phase in purple, the second in orange, which is, that's when the mineralization occurred. 3 is kind of this reddish orange color, and the 4th phase in green. So The drilling results indicate a northwest to west trend to the primary mineralized zones, and the PGE minerals are also present, such as palladium, iron, nickel sulfide, and platinum arsenide. So for the, now I'll move into kind of the good stuff, more of the geophysics. The airborne data coverage at Mayville, there is VTEM data, so a time domain system flown in 2005. In red here, so you can see there's pretty good airborne or VTEM coverage. And this was for initial exploration purposes over the Mayville intrusion. This was flown at 100-meter line spacing with, this should actually say northwest north-south flight lines. And then a ZTEM survey followed up the exploration program in 2010. As you can see, the ZTEM flight lines are skewed a little bit. They're at 140 degrees, also at 100-meter line spacing. And the reason for this was that it was flown more perpendicular to the strike of the ore body once they figured out what that was, which is a little bit more advantageous for interpretation purposes. Here we have the M2 mineralized zone in white, and then there's some kind of a simplified geology in the background. And I'll note that there were 2 other VTEM surveys flown in this area, but just due to what we're looking at, this M2 deposit here, we mostly looked at the 2005 and 2010 VTEM data. So at Turnagain, there is AirTEM2 data, another time domain EM system. This was originally flown in 2004 at 100 and 200-meter line spacing. They did some infill in areas at 40.5 degrees. So there's been more data coverage over the deposit since then, but since we're kind of comparing the AirTEM to the VTEM data, that would be good comparison to use this data set. And I'll note that there is no natural field data here, such as ZTEM or any AFMAG system that we know of, but I'll just be using the ZTEM data for the Mayville property as an added bonus when looking at the deposit. So this is just a summary of what I just said. VTEM data flown by Geotech over the Mayville, and AirTEM flown over the Turnagain. The geophysical data processing included is a calculation of an EM time constant. So that's going to be the time constant tau. We use an adaptive tau or add tau, which is based on a user set noise value and calculates the tau value at 5 values above the noise floor. So since EM induced currents decay relatively slowly in conductive bodies, we can expect an elevated late time tau response with a conductive geologic source and a lower response with resistive sources. And then we also carried out conductor picking on the time domain data, 1D layered earth inversions of the time domain data, 2D inversion of the ZTEM at the Mayville property using a 2D MT algorithm, and then 3D inversion of the ZTEM data using the UBC code MT ZTEM. And all of the processing was done by Daniel Sattel for the EM. And then magnetic grid processing was carried out, as well as 3D magnetic susceptibility inversions using the UBC code. I'm mostly going to be focusing on interpretation for the purpose of this talk, but I'm happy to answer any processing questions to the best of my ability or point you towards someone who can. So our geophysical kind of target model that we're going to start with for nickel sulfides, as I mentioned before, they make great geophysical targets because they commonly occur with conductive minerals such as pyrrhotite, chalcopyrite, and pentlandite. And they sometimes produce a magnetic response, an elevated magnetic response, but direct detection with magnetic methods has been rare in most of the case studies that we've seen. However, magnetic data can be very useful in defining areas of intrusive rocks. And here on the right, we have an example of the kind of simplified geophysical response over the Thompson discovery in Manitoba. I took this out of a paper by King in 2007, which I'll note is a really great paper that goes through more of the geophysical methods such as gravity, radiometrics, etc., for classic nickel sulfide deposits, and is a really good place to start when deciding on which method or technology to use for your exploration program. So overall, EM is great for classic nickel deposits and is a good first pass geophysical tool. The magnetics can supplement in defining areas of intrusive rocks, and then you can kind of window in on your targets that are thought to be mineralized. So for the time domain EM anomaly picking, this example is just over the VTEM data over the Mayville deposit, the M2 we have here. And we carry out the data, or carry out the picking on the B field data. I have one example here of a single peak anomaly over the Mayville deposit. So we go through the data line by line and pick these anomalies, and we're going to be picking single peak here and also double peak responses. And this is kind of the typical conductive body that you'd expect with each response. So for the Mayville, we actually have single and double peak responses, which might indicate kind of a change in geometry of the source as you move along strike. But this is a great example of one of the responses over M2 and something that you can expect over a conductive body attributed to magmatic sulfides. So here we have a depth section, or 2D depth sections through this A to A prime line that crosscuts the deposit area. So these lines are running north-south. The deposit is kind of more east-west trending. The VTEM inversion shows an anomaly that extends to about 300 meters depth, while the ZTEM is actually showing the conductor extending to closer to 600 or more meters. And one thing to note is that the ZTEM is pretty strong in the near surface, whereas in the VTEM, the conductor is starting under a little bit of a more resistive cover. So this could possibly allude to thinner cover than what the VTEM is showing. This just shows the kind of the differing response you get from the time domain system versus the natural field system. And I'll note that the top one is a layered earth, so 1D conductivity inversion, and then the ZTEM is a 3D inversion. So we're getting a little bit more geometric information out of the ZTEM potentially. So the ZTEM is, I guess for those not as familiar, is a natural field system using AFMAG technology, so audio frequency magnetics. And as you can see, we're seeing kind of a deeper conductor. The Z-TEM anomaly here is in orange, and then we have a DXF of the deposit here in pink. So we can extract isosurfaces out of the 3D model, which basically means to extract a 3D volume of a constant value. So here we have two values, one in kind of the lighter orange and one in the darker orange, of two different high conductivity values that are associated with the deposit. So you can see this kind of heel of the actual deposit showing up. And we think that this may represent a deeper system than what's currently mapped by the mineralized zone. And as I mentioned before, this could just be a limitation of the deepest drilling that's been carried out here, but could be interesting to follow up on the mineralization potentially being deeper than what's been reported. So the magnetics, as I mentioned earlier, isn't always directly related to mineralization. So in the top plot here, we have the total magnetic intensity data and the bedrock geology outlined in black. So there are some strong magnetic highs associated with the gabbroic rocks and some of the mineralized area. However, as you can see, the magnetics doesn't directly correlate with the full intrusion or really any of the bedrock geology. The magnetics here can, or the deposit. So it can sort of be used as a mapping tool, but areas of mineralization don't have directly correlated magnetic anomalies, so it shouldn't be the primary tool used for this deposit type. And many nickel deposits do have a direct magnetic signature associated with the deposit or the intrusion. However, here that is not the case. And we do have downhole magnetic susceptibility data here, which is advantageous to compare with the 3D mag results and where the deposit is. Here we have the blue solid is the mineralized zone. And then these blue lines are the drill holes, and these kind of colored discs are representative of the magnetic susceptibility value at those depths. So a larger disc in a warmer color is going to mean more magnetic, while the smaller discs or places where the discs are absent means that there are non-magnetic material there. So this is showing that most of the high magnetic response is in the footwall of the mineralized area. And geologic evidence here shows that the sequence is overturned. So the hanging wall rocks are representative of the lower contact of the Mayville intrusion. And what we found when looking at the 3D model is that it's in good agreement with this result as well. So here we have some ISO surfaces of the Z-TEM and the MAG3D. So again, just extracting one value out of the 3D model that's constant, and it'll produce a 3D volume where that value is present. So in green, we have the 3D mag isosurface. So we extracted a magnetic high, as you can see, kind of in the footwall is where the higher magnetics are. And then we have this Z-TEM heel as well that's trailing off from the deposit. And we have our mineralized zone in pink, and the view we have right now, the mineralized zone, the pink body is kind of dipping away from the screen. So this is a good way to visualize kind of what's going on in 3D, and good way to combine the data sets as well. And for the Mayville, there's also like I mentioned, a PGE zone just to the southwest. Not what we're focusing on today, but wanted to bring up some of the VTEM data that's correlated with PGE zone here. We're seeing a kind of a weaker anomaly, a less dramatic anomaly in the VTEM than what we're seeing in the M2 zone. And then this is the M4 mineralized zone that's kind of above the M2 deposit. So to summarize the geophysical responses over the M2, we have a slight magnetic anomaly associated with the M2 zone, but it's more extensive than just a mineralized area. Generally, there are strong anomalies, but not directly associated with the geology or the intrusion or the mineralized zone. There's a distinct ZTEM anomaly that's apparent in the high and low frequencies, suggesting that the mineralized zone might be under thin cover, but also has that large vertical extent that we saw in the cross section, possibly up to 600 plus meters. And generally, the ZTEM anomaly agrees really well with geologic contacts between gabbros and pillow basalts and quartz diorites. And you can kind of see that here. We have the bedrock geology in the black lines, and this is the 180 hertz in phase ZTEM data. So you kind of see there's a little bit of correlation here with the high response in the geologic outlines. And then the VTEM, there's a very high time constant add tau response around the M2 deposit and the other areas of known mineralization. And the conductive trend contains both single and double peak responses across 16 of the VTEM flight lines. So it's pretty extensive. So now I'll jump to the Turnagain deposit. Just as a reminder, this was formed as an Alaskan-type intrusive complex, and we're expecting less sulfide content here than at Mayville. So here we can see that there's a direct magnetic response associated with the full intrusion, and not as much as a high conductivity response. So it's a little bit hard to see here, but we have the planned pit outline here in green, or sorry, in gray, and in the gray dash line, and that's just kind of representative of where the highest mineralization has been found. And this planned pit outline was taken from the Giga Metals most recent 43101. So while there's excellent agreement between the deposit and highly conductive discrete EM responses at Mayville, we're not seeing the association as clear here. The time domain EM data are kind of mapping out the full intrusive complex like the MAG is, but as far as mapping out the actual mineralized zone, we're seeing a fairly ambiguous, insignificant response. So we do have some anomaly picks, as you can see down here. They're a little bit small, the red and green points. There are some anomaly picks associated with where the mineralization is occurring, but they're kind of trending off here to the northwest. So the EM isn't enough to just define your target or your mineralized zone. And I'll note that the rocks here are reported to be variably serpentinized, which could lead to local variability in the EM response. So here we have a cross-sectional view across the deposit area, F to F prime here in this red line. It kind of goes right across the planned pit outline, which is noted on the in the white dash lines in the cross sections. So the As we saw from more of the plan view maps, the Turnagain has a direct magnetic correlation with like kind of the full intrusive complex, but there is no association with the EM or the mag directly with the mineralized zone. So here we're seeing that high or areas of elevated magnetics could be associated with this WE2 unit, possibly associated a little bit here with the mineralized zone, but overall there isn't much of a direct correlation. And then on the bottom here we have the inversion, layered earth inversion for the EM data, and there's little to no correlation with the mapped mineralized zones here in white and conductivity. We are seeing a near surface conductivity layer that's under a little bit of resistive cover, but this could be attributed to possibly metasediments or a geologic layer rather than mineralization. We can use the magnetic tilt to draw out linear features in the data set. The black lines here are the different intrusive phases that I showed earlier for the Turnagain. There's that phase 1, 2, 3, and 4, where 2 is the phase where mineralization occurred. You can sort of see in the tilt that some of these intrusive phases are outlined, and this could be useful since we know geologically the second phase is attributed to mineralization. It kind of extracts more information out of your magnetic data. So a quick summary of the Turnagain geophysical responses. The intrusive complex shows up as a distinct feature in the MAG and EM data sets and has good agreement with map geology. The deposit area is less distinctly mapped with geophysics. Some EM and magnetic responses of more ambiguous significance here. So to compare the geophysical responses of the two deposits, magnetic data over the Turnagain highlights the intrusive complex that's related to the mineralization. The Mayville intrusion that's related to mineralization is a lot less obvious in the magnetic data. There's direct correlation with a discrete bedrock conductor and the Mayville M2 deposit, whereas the Turnagain mineralization does not have a clear conductivity anomaly that's just associated with the deposit. So one of the pieces of the paper was to give implications for future targeting, because we can look at case study after case study, but kind of wanted to bring out something that is useful looking forward when conducting nickel exploration programs. So airborne EM methods remain useful in traditional magmatic sulfide nickel targeting, such as what we saw at the Mayville, and AFMAG methods such as the ZTEM may allow for deeper mapping to identify large mafic and ultramafic intrusions. So the VTEM is a great first pass to time domain data, and then the natural field systems could give you more geologic information and more depth information. The Alaskan-type intrusive complexes and convergent margin settings can be prospective for economic nickel mineralization, but this is kind of just given the right geologic ingredients like what we have at the Turnagain, where the intrusion interacted with sulfur-rich rocks, host rocks during the kind of second phase of its formation. EM can be an effective tool for identifying intrusive complexes and has potential to highlight mineralized zones, but we can't and perhaps shouldn't expect mineralized zones to produce an EM response in these kind of more unusual nickel deposit settings. So potential follow-up methods could be high resolution mag data over Alaskan type intrusive complexes may better reveal those intrusive phase boundaries with implications for more prospectivity. Use of DCIP, so ground geophysics, could be effective for mapping lower grade, high tonnage, Turnagain-like nickel deposits. And then always your geologic mapping remains an effective supplemental tool to see what you're seeing on the ground and hopefully correlating with your geophysics. So to wrap it up, airborne EM surveys successfully identified conductors associated with copper nickel mineralization on the Mayville property, while on the Turnagain it was more successful in mapping the full intrusive complex. Airborne EM and MAG remain good first pass geophysical tools for nickel exploration for both types of deposits, and then your follow-up with ground geophysics is important as well for more high resolution data. Convergent margins may represent an underexplored region with high nickel prospectivity. These could potentially be more lower grade or higher tonnage targets, but as we're seeing growing demand for nickel, finding more deposits and mining these lower grade deposits could be economical. Detecting large mafic and ultramafic intrusions undercover can be a good first step in a nickel exploration program. And this is basically highlighting the importance of studying different deposit types to add value to your nickel exploration program. All right, so I just wanted to give some acknowledgements. Thanks to Grid Metals and Giga Metals for allowing us to use and present the data. Thanks to my co-author Blake Cross and my boss Ken Witherly and everyone at Condor for supporting this work. Thanks to Daniel Sattel for doing the EM inversions for us. Thanks to Geotech for collecting and providing us the data, to the SEG for allowing us to submit and accepting our paper, and to everyone at the MTNet group for putting this together. And here's my contact information. And we'd love to get more eyes on our paper if you subscribe to the Leading Edge. So we're open to any further suggestions or questions on that. And that's all I have.
Yeah, thanks very much, Hannah. Absolutely wonderful to see these two different projects. And just while the questions roll in, and we have a couple already, just a generic one. Is there anything in the data that is still unexplained? And what I'm particularly wondering is I'm seeing in my work that I'm doing for companies these days, I'm seeing more and more evidence for electrical anisotropy. And I'm just wondering whether there was any evidence in your data. I presume these are isotropic conductivity inversions, but I was just wondering whether there's something in the data that you couldn't explain.
Trying to think. Yeah, I think as far as the ZTEM data goes, the natural field system, we're kind of questioning why we're seeing that conductor go so much deeper and kind of more trailing off towards the south. And that just might be the difference in limitations between the 1D inversion and the 3D inversion. But as far as all the drilling goes, we haven't seen anything deeper. So that's one thing that we're maybe hoping to answer in the future. And your comment about the anisotropy, that could be another thing we would look at in the future. But as far as further questioning, might have to get back to you.
Yeah, sure.
Yeah.
Sure. Well, we have First question came in from Benoit Tournier, and it's a question that I have as well. If we could just roll back to your VTEM, ZTEM, as I would say, up in Canada here, we say ZTEM. ZTEM inversion.
Sorry.
Yeah, was that it? The
Maybe this one?
that one, yeah. What are the units on the ZTEM? Those are weird units.
Yeah, I think that's actually an effect of the program I'm using to plot. The units are millisiemens per meter. So you can expect them more to be in this range of 0 to 1,000 for activity, but this scale bar might not be representative of the actual values. It gets a little funky when you plot it as a histogram. So that might be something I need to fix on the plot, but we can expect the ZTEM values to be kind of in the 1 to 100 millisiemens per meter range.
Yeah. Fernando Zamudio says, hi, Hannah, thanks so much for your talk. Please, can you describe the add tau parameter? I'm not familiar with it. Thanks in advance.
Yeah, so the add tau is the EM time constant. So here we have in this plot on the right is the decay curve for the EM, or a typical decay curve for the EM time domain system. We have time on the x-axis and the X channel on the y-axis. So you're seeing your different time gates here. Here we have plotted 7 through 19. So we're calculating the time constant, which is it was calculated based on the later time EM decay. And it's basically representative of the EM decaying in conductive bodies. So if you have a higher response, a higher add tau response, you're gonna be indicative of a conductive geologic source. If you have a lower, little to no response for the add tau, it's going to be indicative of a more resistive source. And I hope that's a good explanation, but also Daniel Sattel, who does this calculation, I can also point you towards him. He might have a more in-depth explanation of how he does these calculations.
Yeah, we'll jump over a question now because it's very long and we'll get back to it.
Yeah.
Alan King. Hi, Alan. Great to see you here. What about low sensitivity of the AEM, TEM to high conductance magmatic sulfides with tau much greater than 100 milliseconds?
Sorry, I'm just reading the question. Conductance.
Oh, I see Alan has his hand raised. So
okay, yeah, I'm not totally sure what the question is there.
Yeah. Alan, I've just allowed you to talk.
Okay, can you hear me?
Yep, yep.
Yeah, like the age-old problem with airborne for magmatic nickel sulfides is that the really massive good ones are extremely conductive, so and large, hopefully, and possibly deep. So the tau gets very large, and if it can be over 10, 100 and more milliseconds, and they become almost the main core becomes almost invisible to airborne EM systems, not to ZTEM because it measures during the on time, but it's a sort of fundamental problem for magmatic sulfides for off-time TEM systems.
Right. Yeah. I guess so. Are you asking if we experience any low sensitivity of the high conductance, or
well, the problem is you just don't see them.
Right. Yeah. Yeah. And there was
it's just
go ahead.
It's just worth mentioning.
Yeah,
Go ahead.
that is worth mentioning. In the paper, forgot which slide it's on, by King. Forgot where I have that slide. Oh, here. He mentions that in his paper. We have this AEM signal here, but he mentions that different systems and systems that, for example, only use the off times can miss some of the high conductance magmatic sulfides. So yeah, I really liked his explanation of that sometimes there is low sensitivity, such as like what we're seeing here.
Yeah, that is, you are actually talking to the king who wrote the paper.
Oh my gosh. Sorry, I can't, the chat box, I have to keep putting it away so it's not in my way. Thank you.
No, it's no problem.
Thank you for your paper. It's great.
Yeah, you're welcome. I'll send you some of the summaries on it. It's a bit of a niche thing, like all this stuff, but I'll send you a couple more recent summaries.
That would be great. Thank you so much. And
Yeah, great. Thanks, Alan.
Yeah.
Okay, we have a very long question from Deloro Fitlo, and I do need to read it out so it gets into the recording. I'm interested to know if magmatic inversion techniques were employed in the analysis, considering the presence of remnant magnetization in magmatic nickel deposits, which can influence the magnetic response. I would like to inquire about the extent to which remnant magnetization was considered and accounted for in the inversion process. During the presentation, you mentioned the use of inversion techniques for interpreting airborne EM data. I'm particularly interested in how you address the quantification of uncertainty in your inversion results. Well, don't we all? Could you please provide insight into the specific regularization scheme employed and how it contributed to quantifying and managing uncertainties in interpreted models? I'd also like to pose a question regarding the choice between deterministic regularization and Bayesian inference in geophysical inversion techniques, considering that regularization is deterministic based on prior knowledge and constraints, while Bayesian inference is stochastic. Yeah, so a lot of very generic issues there that we're dealing with in inversion, but perhaps if you just want to address the first part.
Yeah, so the magnetic inversion, actually all of the inversions I personally did not do. So I'm not sure if I'm the best person to address some of the specifics, especially in the second part of the question, but I could point you towards someone who would be able to answer that. But as far as remnant magnetization goes, when we do interpretations of the models and the data, we're always cognizant that could be the case. But as far as it being considered and accounted for in the inversion process, I am probably not the best person to answer that question, but if you send me an email, I can point you towards who runs the inversions, and they might be able to better answer your question, or I could get an answer from them and let you know. But thank you for your question.
Yeah, I think all these different inversion codes have different approaches, and each of them has their own strengths and limitations, and you need to understand those when you're running these codes. Yeah.
And I'll point out it was done using the UBC GIF 3D code. So I'm not sure if they have documentation on how that's accounted for in their inversion.
Sure, I'm sure Lindsay would.
Yeah, Lindsay might be able to answer that.
Yes, I could jump in on that. There are two codes, or so there's one that will invert just for susceptibility, but there is also an MVI code that will invert for the vector magnetization. So that can be used if you expect remnants, but it's a question of kind of what are your expectations, and what do you want to try and get out of the data? But both codes do exist, and yes, there is documentation. If you look up Mag 3D on Google, there's documentation around. But you can also ping me on that one if you like to.
Thanks, Lindsay.
We have a question from Manish Kumar. Thanks, Hannah, for your presentation. What was the base frequency of the Airtem system? Did you think that perhaps it is not looking deeper as ZTEM or VTEM and hence no response from mineralization?
Yeah, I was just actually looking. I have the base frequencies written. Give me 1 second. I know the VTEM system is 30 hertz. The base frequency for the Airtem system is 150 hertz. So it's a little bit higher frequency, but yeah, that is a possibility. As like we see with the Mayville, the ZTEM is recovering a lot deeper information. So it could be that the Airtem is for the Turnagain deposit is only recovering nearer surface information than what's needed to find the conductive response for the mineralization. So it would be interesting to have a natural field system or even VTEM, which is a little bit lower frequency over that area to see if anything is responding differently, or even something like a ground MT over the known mineralization to see if there's any conductive response from that.
Yeah, I guess you could move towards joint inversion of the VTEM and ZTEM, or if not joint inversion, then cooperative inversion. So you move backwards and forwards because they're both sensitive to conductivity, right? So
yeah, the joint inversion would be a great idea.
Lindsay, you wanted to jump in?
Sure, I'll jump in, actually, kind of picking up on this topic a bit too. So a lot of your the Airborne EM, the time domain inversions were all 1D. Have you ever looked at 3D inversions or potentially see value? Is that something you guys are exploring at all at any sites? Or if you could follow up here with 3D inversions, what do you think that might add?
Yeah, I think that would be a great idea. We're actually considering using the new 2.5D time domain code on some of our VTEM data, which is I know more of a new inversion code. So we haven't played around with it much yet, but we are hoping to use that code to extract more geometric information out of our time domain data. So yeah, that's definitely something we are looking into and would like to do in the future.
Cool. Yeah, because at the Mayville, I mean, you saw sort of the classic pant legs. So it strikes me that, perhaps especially too, as you're talking about asking how deep does that conductor go with the ZTEM, the VTEM in 3D provides some interesting insights.
Right. Yeah, exactly. Thanks.
So, thanks, Hannah.
We have a question from Seshu Davathu. Sorry, I'm mispronouncing your name. How can we identify superparamagnetic effects of EM anomalies in the VTEM and ZTEM data?
That is actually something I'm not as familiar with, and I'm not sure they can clarify that question, or if it's something I can maybe get back to you on. But
Yeah, that's an interesting question. I need a moment to think about that, but I wouldn't have thought that superparamagnetism would necessarily give you an EM anomaly.
right. Yeah. Yeah, I'm not sure if that wasn't considered in the study that we did, but maybe if we looked a little bit deeper into these two data sets, it could be something to focus on.
Yeah, a very interesting question now from Sina Kamyab. Just a general question as someone who's new to the EM world, wondering if newer EM airborne techniques could in any way improve the results, or it would be mainly limited improvements to the data and more work has to be done in enhancing the inversion algorithms.
Yeah, so as far as the EM technology, We're still seeing a lot of data collected with the VTEM system. I think at this point, the AirTEM system might not be used anymore, but the VTEM data that we see now is has a lot less noise, and inversion of that could definitely improve the results, and as well as with the anomaly picking, it's a little bit easier when your data is less noisy. So any newer time domain system could definitely improve the results. The ZTEM data is also a newer system relatively, and having that natural field data incorporated definitely improves what we can interpret out of the data, and like Alan said, could be an opportunity to do some joint inversions. I am not as familiar with what's been done in enhancing inversion algorithms. That could be another question for Lindsay, but assuming that there has been some improvements to inversion algorithms since such as 2004 when this data was collected. But to my knowledge, so such as the ZTEM code, the 3D was redone just this year. So we are using the most up-to-date code that we have for that.
Yeah, I think, you know, with all Airborne EM methods, there's going to be sort of limits to what you can do with the data. And at the end of the day, as you said in your conclusion, you have to get boots on the ground, and you were talking about geology boots, but I think you need geophysical boots as well and get land-based EM data. And that leads into a question actually from Bill Thuma, who says that TDM seems limited here. Do you think mobile MT may offer some advantages? Have you looked at this as an alternative? And can you elaborate on what ground methods would be recommended?
Yeah, so mobile MT could be considered in both places. We already have the ZTEM data over the Mayville, which kind of provides a similar data set to mobile MT. I know there are some differences, but providing the natural field data. So like I was saying earlier, maybe a natural field survey over the Turnagain deposit could be really useful to see potentially deeper than what the AirTEM system is seeing, and the mobile MT is a great option for providing the passive or natural field data set. So that could be a suggestion to make to the exploration company if they're looking for any further surveys to fly. And as far as ground surveys, ground MT is always great if you're looking for deeper sources. You could do time domain EM on the ground, which could give you a little bit higher resolution information than just what you're getting out of the airborne time domain systems. So I would say either of those. And like I mentioned for the Turnagain deposit, since we are seeing pretty good correlation with the different phases in the for the intrusive complex and the magnetics, having a higher resolution magnetic data set could be useful there if you're wanting to do some closer mapping to the geology. So.
Yeah, but of course, I'm going to advocate that you should be doing magnetotellurics.
Yeah, and there's options such as, you know, controlled source EM and AMT. So there's a lot of great options that you can do with the MT system, depending on how deep you want to see and what your deposit is. So. There's
a comment from Tyler Matheson, and thanks Tyler for this. Further to Seshu Davartu's comment, I have seen magnetic viscosity occur in on-time low-frequency B field systems. Neither ZTEM or VTEM go low enough. Less than 8 hertz is needed. So I guess that answers the previous question about paramagnetism.
Right, okay.
Okay, any more questions? Lindsay, do you want to jump in with any more, or?
Just thanks to Hannah. I mean, it's great to see examples of, you know, the interpreting data and the real world use of geophysics for mineral exploration. So very much appreciated it.
Yeah, thanks. If there's no more questions from the audience, I see people are clapping. So well done, Hannah. Absolutely brilliant.
Yeah, thank you so much.
Yeah, hopefully we'll have you back in season 4 for an update on new work. Okay, thanks everybody, and I'll see you same time next week. Bye. Thanks, Hannah. Oh, and Hannah, could you send me your PowerPoint?
Yeah,
and then this recording will be available on the website in about an hour or so. Bye, everybody.